Hello everyone, welcome to our daily physics problem, day 17. So today we have a U-shaped wire of mass m, has its end immersed into two jars of mercury, which are separated by a distance L. Mercury is just a part of the wire conductor. The wire is a uniform magnetic field, B, vector perpendicular to the plane of the wire and pointing into the plane page as shown in the figure. A very fast current pulse in the path through the wire, and as a result, the magnetic field creates a very short impulse of force on the wire. In response, the wire acquires upward velocity. The wire is observed to move up to a height v, a height h, at which point it stopped and then fell back down. How large was the total charge which passed through the wire from the beginning to the end of the current pulse? And we have hint is the total charge equal to the integral of current over time, and the impulse, uh, the change of force over time, is equal to the change in momentum. So I want you to pause the video, try your own. After you try, come back to the video and show you how I did. So welcome back, guys. So first, when we look at this problem, let's find some relationship. That's what physics do. We find a relationship between objects. So in this problem, we know the height which the wire goes. We know the mass. But we can try to find the relationship between potential energy, gravitational potential energy, and the kinetic energy to find the velocity. Then we know the velocity, we can find the momentum. And from the momentum, we know the change in momentum. We can know something about the force, the impulse of force. Then we know force is magnetic force. We can relate force with magnetic field and with the current. And after we relate it to the current, maybe you can find something about the charge. So let's start to think about the equivalency of energy first. So first we have mgh equal to 1/2 mv squared. Then we know v will be equal to 2gh and the square root. So after we know v, what is the momentum? We know momentum is equal to changing momentum equal to the momentum after minus the momentum before. So the momentum after will be equal to mv2 and momentum before is mv1. And what is mv? Oh, that should be mv1. So initial velocity, the final velocity is 0, so final momentum is 0. So all the momentum conserved. So we know that momentum will be equal to m times the square root of 2gh. We know the change in momentum. We can relate it to impulse. We know impulse is the integral of force about 2t. Then we know force is the magnetic force. What is the magnetic force? In a wire is the integral of I to the line integration variable to the cross product of the vector of the magnetic field. And here the magnetic field is uniform. So what is the integral of our current over its line integral? Well, we know the cross product of B with our direction of the wire. We know D is pointing downward into the plane. So, and we found the cross product. We only need to consider the sign part. We need to consider which of them are perpendicular to each other. So, in here, we are only considering this segment of the wire here. As other wire, they just don't do any work. They cancel it out. One to the left, one to the right. And only this part was useful. And we know because we only care about where they are perpendicular to each other. So we can ignore the curvature. Just think about L. Instead of pi L, we just think about L. So the magnitude of the force will be equal to I times B times L. And the direction will be to upward direction because it's being lifted up from the floor. So now we can plug our force back into our impulse equation. We have m times the square root of 2gh equal to the integral of I times b times l times dt. Then we know I, b, l are just constant. So we got mg times square root of 2gh divided by bl is equal to, because we know this hint q is equal to the integral of I times dt. So we can know Q will be mg times 2gh divided by BL. Oh no, there shouldn't be a g, so just m times the square root of 2gh divided by BL. And that's our final solution.